Good morning and good afternoon, everyone, and welcome to today's Exploring by the Seat of Your Pants event. My name is Joe Gorowski, and I'll be your host for today. Let's see. Wow, we're already halfway through May. I can't believe it. May, we always have a big theme of biodiversity, so we've had some great connections with scientists, conservationists, and researchers from around the world. We've got our big Global Biodiversity Festival for the general public coming up on the weekend, and still lots more May events to come for classrooms. So if you haven't already, take a few minutes and visit exploringbytheseat.com. You can find all the events that we have coming up and how to register. And of course, I want to draw your eyes to June. I know June might seem like a long way away, but we're going to blink and it's going to be here. And June, World Ocean Week, we have an incredible series of live events coming up. So if you visit exploringbytheseat.com/Ocean Week, you'll find there. And in fact, there's still more events to add to that list. So it's going to be a jam-packed Ocean Week as we race towards the end of our school year in the US as well as Canada. So great event coming up today. Quantum mechanics, it's a big word for many classrooms out there, but it helps us understand the incredibly tiny world of atoms, electrons, photons, and more. And we have an awesome guide to kind of take us a little bit into that world, to illuminate the science of light for us. We've got Dr. John Donohue joining us from the Institute for Quantum Computing at the University of Waterloo for some fun learning about light particles and electron waves, quantum computers, and things like that. But he's going to illuminate this world for us with some fun light experiments today. So I'm going to bring John in live with us right now. Hey, John, how are you?
Not too bad. Thank you so much for the introduction, Joe.
Yeah, of course. John, it's great to have you joining us. We always enjoy stealing a little bit of your time. I should want to give a shout out to the classrooms who are tuning in right now. Use that chat sidebar. Let us know where you're tuning in from. And of course, we're looking forward to your questions a little bit further on into the chat. So John, we'll let you take over for a bit and then we'll go from there.
Sounds great. Thank you so much. And thank you so much to everyone joining us today. My name is John from the Institute for Quantum Computing at the University of Waterloo, here to talk to you today about the science of light. So yeah, lots of biodiversity activities, lots of things along that line going on in May. But today in particular, we're going to steal away from that a little bit because today is the International Day of Light. May 16th, every year, the entire scientific world celebrates the Day of Light. That's where we talk about the different things that we use light for, the different experiments that we build to study light, and the different technologies that we build that really rely on us understanding what light is. So light I always found to be a pretty fascinating subject because it's something that is absolutely everywhere, right? I mean, it's one of the first things we notice when we are born is we try opening our eyes and we realize, oh, that's bright, that hurts. We're not dealing with that. Light is something that we all have a fairly intuitive understanding of. It's, what helps us see. It can make things hot. But when we start asking the scientific question of just what exactly light is, we run into some complicated answers very quickly. And that's actually one of the reasons that I got into physics in the first place, is I was really fascinated with I have a background in physics, and physics is where you start asking some of those questions about what the universe is, what builds it up, and how we can actually describe it, and how we can predict how the universe behaves. And light in particular is one of the things that when you start learning about those details of, it gets complicated and it gets interesting. You start learning about things like Einstein's theory of special relativity, which tells you that the length of time that you perceive is somehow, in some inexplicable way, related to the speed of light and how fast you're traveling relative to another observer, and how you perceive time may differ depending on that relative speed. And it all ties back to light being what carries that information. It's fascinating, mind-boggling stuff. And when I started studying it, that told me, okay, I want to be a theoretical physicist. I want to spend my life immersed in math equations to figure out exactly how things like light work and how things like quantum mechanics work, the study of atoms and photons and electrons and all that stuff that's going on below what microscopes can image. What happened is I started doing some research and realized I don't really like the math equations too much. Don't get me wrong, I like them, but I don't like doing them all day, every day. What I really like is taking some of those ideas and finding ways that we can build experiments to test them. So these are some of the experiments in these pictures here that I've worked on before, all using very high-powered lasers to actually learn things about quantum mechanics. So basically what we do all day in optics labs where we study light science for quantum mechanics is we'll take a bunch of optical Legos, mirrors, and lenses and laser beams, use them to build up to some sort of experiment where eventually we're going to detect some very, very small signal and learn something about the universe. In my case, learn something about quantum mechanics that maybe either helps us understand the world better or maybe helps us build new kinds of technologies. We'll talk about some of those technologies in a bit, but before we start talking about uh, how we use light, we should probably just talk about first what is light. So as mentioned, it's something that we all have a fairly intuitive understanding of what light kind of is, but what is light really? What is it about light that allows us to see or allows us to communicate? If you're getting this lecture through a fiber internet connection, it's actually light signals that are being exchanged in that connection that are allowing you to see this signal, which are then creating light from your laptop screen, which is being processed by your brain. It's all light all the way down. So the question of what light is, well, what's one of the first things that we learn about light is, well, okay, we learn that it carries energy. Okay, and there's lots of way that we can use the energy from light. The first time you might have seen this is you go out on a hot day and you start eventually correlating that. Well, when it's a hot day, it's also a bright day. The light from the sun is what is heating up the earth, and it's what's allowing us to, frankly, live. The fact that we get that heat from the sun, that it travels from the sun to the earth in the form of light, but we also use the energy from light in many other ways. You might have held your hand up to a light bulb and noticed that it gets hot because the light is carrying away energy from that light bulb. You might have noticed that when you turn a stove top on, it starts glowing red. The energy is radiating off that stove top, and some of it is radiating as red light. Microwaves, they don't look like they use light, but really what they do is they create a high intensity field of microwave light, which is just the same thing as the light we see with, but at a what we call a lower wavelength where our eyes don't perceive it. We can use very, very high powered lasers for laser cutting. We can do infrared imaging. In all these different ways, light is carrying energy. But the question of how light carries energy is something that actually boggled the minds of many scientists for quite a while. So there were two basic schools of thought about what light, how light carried energy, sort of throughout the 1800s, let's say, so about 200 years ago. Either it could have carried it as a particle. So think about a particle like sand or marbles. If we think about light as carrying energy as these little tiny blips of energy, think about like a little tiny tennis ball. Every time there's a beam of light, and it's just made of all these little tiny particles that carry that energy. And the other option would be that it would carry light's energy as a wave. Okay, so similar to a water wave. Now, when we start thinking about particles versus waves, we usually think about these as having two different kinds of properties. So, for example, a particle, if I have like a tennis ball or a marble or a grain of sand, it only exists at one place, right? I can say with certainty that the tennis ball is here. Meanwhile, if I have a wave, like a water wave, it spreads out over a large amount of space. Think about a sound wave. If the sound waves that are coming out of my mouth, projecting out throughout this room, they're spreading out over the whole room. So we can't say the sound wave is here, it's everywhere. Particles have properties like mass and volume. Waves have properties like wavelength, amplitude, and frequency. If I have two particles and they collide with each other, they tend to bounce off each other. We have kinetic collisions. If waves meet with each other, we might see something else like wave interference. And just fundamentally, a particle is countable. I can look at a particle, I can look at a tennis ball or even a handful of sand, count it up grain by grain, and say, I have however many particles of sand in my hand. But waves are continuous. If I have a wave that's like this versus a wave like that's like this, I might be able to say, well, one's twice the amplitude of the other, but I wouldn't say I'm able to count the number of waves there, right? We wouldn't ever say that. So what kind of things does light do? And is light a particle or a wave? So let's dive into one of those wave behaviors and see if we can make light do the same thing. So think about water waves again. I drop a rock in a pond, it creates ripples, and those spread out. Okay, so they start waving, they're going up and down like this, but they're spreading out from that center point. Now I take two rocks and throw them in the pond at the same time. The waves from one rock are going to spread into the waves from the other rock. And now, if the waves meet and they're both what we call in phase, they're both going up and down at the same time, then they're going to do what we call constructively interfere and make an even bigger wave. But if they're opposite to each other, when one is up, the other's down, when they meet, they're going to cancel each other out. We're going to be left with no wave whatsoever. We see that in this image here. We see these areas of constructive interference where we get even bigger waves starting from the two sources. And these areas here where the waves actually cancel each other out and we're left with no wave amplitude whatsoever. This is what we call wave interference. Okay, now can we see this with light? If light is a wave, if that's the way we want to model light, we should be able to see interference as well. So, the experiment that was actually devised by Thomas Young in the 1800s to put to bed the debate of whether light was a wave or a particle was to indeed do exactly that. We're going to take light and we're going to make it so that it appears as if it's coming through two different sources, similar to throwing two different rocks in the pond. So, we did what's called the double slit experiment. We take light and we shine it through two very, very narrow openings called slits. Light can go through one slit and then expand outward beyond that slit. It can go through the other slit and expand beyond there. And what's going to happen is the light from one slit is going to expand into the light from the other slit. And if they meet further down the line and they're in phase with each other, they're both going up and down at the same time, we'll get an even brighter wave than before. And if they're out of phase, they should cancel each other out. This was actually a pretty difficult experiment to do in the 1800s. You had to get something called a coherent source of light, which is trickier than it sounds. But we have very, very cheap coherent sources of light today in the form of laser pointers and laser beams. So we can do that experiment very, very easily. We take the light, we shine it through the double slit experiment, and we see some places on the screen far away where the light is very, very bright. That's our constructive interference. In some cases where it's completely dark, the wave cancels itself out. That's our destructive interference. So we can look at an experiment like this and say that, okay, light is behaving like a wave. If we model light as a wave, we can understand some of its properties. Okay? So light's a wave, but what's actually waving? So if I throw a rock in a pond, that creates a wave, and the wave is the water molecules being displaced and going up and down and up and down. If I speak, that's a sound wave, and the wave is that the air molecules in the air are vibrating at the frequency of whatever sound I'm making in my mouth. So what is actually waving when we deal with light? Light is what we call an electromagnetic wave. So, if I'm a beam of light coming from this flashlight, for example, what's actually waving is an electric and a magnetic field, the kind of things that charges feel and can make electricity move around. So, for example, the beam of light's coming out this way, we got an electric field that could be waving up and down like this. It could also be waving side to side like this. Okay, so light from a flashlight or a laser can travel in a straight line and it waves up and down like this. We can also have light that spreads out in all directions. Think about light from a light bulb and it's kind of waving out like this. You know, it's going everywhere, but it's still waving up and down or side to side. Now, it could be up and down, it could be side to side. The direction of that wave is what we call its polarization. Okay, so don't trust me on the fact that light has polarization. Let's investigate it a bit ourselves. So I'm going to switch over to the demo camera real quick. And what I have here is something called a polarizer. Okay, so this is a special sheet called a polarizer. You can get them from Polaroid sometimes. And what it does is it absorbs light depending on its polarization. So if I'm a beam of light and my polarization is like this, if I meet this polarizer, I'm going to be absorbed. But if I'm a beam of light and my polarization is side to side, horizontal polarization, I'll be able to travel through like there's nothing there at all. Now, you might say, okay, I start rotating this polarizer around and really nothing seems to be happening, right? Well, that's because the light around me is unpolarized. It doesn't have a specific direction to wave in right now. It's kind of waving around in all directions, mostly randomly. But if I take this polarizer right here, I'm just going to put it right there. So it's standing in between us now. So now what this polarizer is doing is letting through all the light going this way and blocking all the light polarized in this direction. And now if I take a second polarizer and hold it the same way, once again, doesn't appear to be doing much. But if I start rotating it like this, we see that it blocks my face entirely out. If I rotate it back, you can see again, and now it's blocked out. The reason is that this front polarizer is blocking all the light that's going up and down. It's blocking all the vertical polarization. And this polarizer here is blocking all the horizontal polarization. If I block all of one polarization and also block the other polarization, I'm left with no light whatsoever. So, this is one of the ways that we can investigate the direction in which light is waving and actually start using that to build different things. And okay, so we often think about this in kind of this gate fence model. So, for example, we can have polarizers, and if they're aligned towards each other, it's like having two fences that are aligned parallel to each other. Any waves that make it through one fence also make it through the other fence. When I have two polarizers that are 90 degrees to each other, then it's like having two fences that are also perpendicular to each other. A wave can make it through one fence, but will get blocked by the other. Now, you can see this for yourself. If you have a pair of polarizing sunglasses, you can try this out on your computer monitor. So I mentioned that most sources of light are not polarized. Light that comes from the sun does not have a particular polarization. We need two polarizers to see this effect. But light that comes from computer screens and certain other surfaces, certain other emitters, actually does come out with a distinct polarization. The polarization is actually how we control which pixels we see on our computer screen. So if you get a pair of polarizing sunglasses, which most cheap sunglasses are not polarizing, but most prescription sunglasses are polarizing. And you twist them around in front of your laptop as you see on the screen there, you should be able to see that you can block out the light or let it through. This is one of the ways in which polarization is applied in real technologies. So it's used in photography as well as sunglasses to reduce glare. Light from the sun is not polarized, but it turns out that light that is reflected off of a surface picks up a polarization. It's more aligned in one direction than the other. This is what we call Brewster's effect. Okay. So if I look at a lake through a polarizer, I'll be able to see through the surface more efficiently. And in this case, they're using it to see the fish beneath the water without just measuring the reflection off the surface. It can also be used to reduce road glare when driving. So this is why polarized sunglasses are really, really useful when you're driving a car because it's going to reduce the road glare on wet days without reducing too much of the other light around you. It's also used in 3D movies. What they'll do is they'll put two different polarizers on each of the glasses in the movie. And what that'll do is that will allow you to see two different images. So three-dimensional 3D movies, what they're really doing is faking it so that it looks like the object has depth by making sure your left eye and your right eye see a very slightly different image. And the way they do that is they project two images on the screen. One has horizontal polarization, one has vertical polarization, and they make sure that the vertical one is only seen by one eye, the horizontal one only by the other eye. And it's also used in these LCD screens. It's actually very, very difficult to turn a light bulb on and off very quickly. Like our eyes will be able to tell that something's not quite right there, but we can flip polarization from horizontal to vertical very quickly. So what we do is we have two cross polarizers, so it's normally a black screen on our laptop. But if we want to say let this pixel show, we'll quickly flip that polarization this way, allow the light through, and that allows us to very quickly change the image on our LCD screen. That's what gives us this frame rate that we're currently enjoying. Okay, let's see how we can actually investigate this a little bit more. So I'm going to go back to the demo camera. If I can find my mouse, there it is. And what I'm going to do this time is I'm going to pop open this bit here. So this is basically an LCD screen. It's a special polarized light surface. What doesn't really look like anything right now, but if I put the polarizer over top of it, we can see that indeed it is polarized. I can block it out at a certain angle. Now, one thing that we can use polarizers for is for analyzing materials. So this right here is a plastic fork, the kind of thing that you might get from the dollar store if you're hosting a large dinner party. I'm going to put that on top of the polarizing material. Now, this fork is made out of plastic, and what they do with the plastic is they extrude it and mold it into one specific shape. But there are certain pressure points in the plastic where it might be weaker than other places. So we're going to take that and we're going to look through it through the polarizer. And it might be a little tricky to see, but we see some colors start to show up right there, right? We start seeing some patterns. Yeah, right there, it's much more obvious. And these patterns, if we analyze them just right, can tell us where the pressure points in the material are. So we can use this idea of crossed polarizers to start to understand uh, where some defects and otherwise weak points in materials are. This is an effect we call birefringence. What it basically means is that when I have a plastic like this, it can actually rotate the polarization. So something that was polarized side to side might flip and rotate to up down vertical polarization. Now, plastic forks are one thing that do it, but a lot of other plastics do as well. For example, if I take a piece of tape, so this is just regular, invisible, transparent tape. I'm just going to take a couple pieces and I'm going to put them on top of this piece of plastic. Now then, right now, because that light is so bright, you basically can't see the tape I put down. You saw me take out the tape, but you really couldn't see me put it down there. It just looks like a white screen. But if I put the polarizer on top of it, we see that the tape rotates the polarization. And depending on how many layers of tape it went through, we see different colors appear through the tape. Now, I could spend a while making one, but I actually got that done earlier. So this is a bunch of tape on an old CD case. And if we look at it through the polarizer, we see this wide array of colors, right? And that's because different the polarization rotates by a different amount depending on how many layers of tape it went through. You can even, instead of just randomly structuring, you could start putting in little secret letters. So, for example, right here, I've put a secret Greek letter psi, which is a particularly important one in the field of quantum mechanics. Okay, and if you have a lot of time, you can start doing things that are even more complicated. So this is an artist named Dino Tomic, and you can find his full video there. But you can see that he spends a lot of time here just cutting pieces out strip by strip, putting them on this very, very large piece of plastic. And if we let that go for a little bit longer, yeah. So we'll see, doesn't look like a ton, looks like just a bunch of tape and gunk. But if he looks at it through the polarizers, we see this image start to appear. So if you're very, very careful about how you place that tape, you can start making very, very complex shapes and patterns. We can also get stained glass effects. For example, in this video here, oh, I have to press play, where using polarizers. So one without the polarizer, it doesn't look like anything, but with the polarizer, we see this very, very cool stained glass pattern. And remember, what you need to do this is you need a polarizer, some tape, and a polarized screen. If you have a pair of polarizing sunglasses and you have a laptop screen, you can do this yourself at home. You can check it out. We have some instructions for how to do that yourself at tinyurl.com/polarization art. So if you're just in a little activity, making some secret art that only you can see with your special polarized sunglasses, you can definitely try this out yourself at home. So one of the questions you might ask is, why was that colorful? Well, light does have a color. So the color of light is actually connected to its wavelength. So if I'm a beam of light, I'm a wave, I'm going up and down like this. I could be going up and down like this however many times per second, or I could double that and have a wave that goes faster and faster and faster, has a higher and higher frequency. Now, we tend to associate with other kinds of wave that frequency with energy. For example, we know that sound that has a low tone has a low frequency, whereas high pitched noises have a higher frequency. Similarly, light that has a lower frequency would be associated with lower energy light, like red light, for example, has the lowest frequency of the visible spectrum, whereas something like blue and ultraviolet light have very, very high energy. They have very, very high frequencies. Okay. So white light is actually a combination of all the different colors. So what we have here in this GIF is we have a white flashlight and we put it through what's called a diffraction grating that separates out the colors. And we see that this white light is actually made up of blue light and green light and red light. So white light is not anything by itself. It is a combination of many different colors together. And all of these different colors have these different wavelengths, red light having a longer wavelength, blue light having a shorter wavelength, and everything in the middle having some wavelength in the middle. So all across the visible spectrum. But indeed, there are light colors of light outside of what the eye can see. The visible spectrum is only a tiny slice of the entire spectrum of light, the entire spectrum of electromagnetic waves. This little slice in here between, let's say, about 400 nanometers to 650 nanometers. So that's 400 billionths of a meter to about 600 billionths of a meter. That's the wavelength of visible light. If we go a little bit to one side, we get to infrared light. That's just too long of a wavelength for our eye to see, but used often in things like television remotes, infrared imaging, fiber internet connections. They all use infrared light. We go a little bit further, we get microwaves. That's used in radar, for example, and microwave ovens. Go a little further, we get radio and TV waves. So those are the waves that come from those giant radio towers that really spread out over long distances that we use in our cars to pick up radio signals. If we go to the more energetic side, we get to ultraviolet light used in a lot of fabrication processes and also being emitted in large amounts from the sun, which is why we have to wear our sunscreen in the summer. X rays, which are very energetic, that we use to image inside our bodies, and gamma rays, which are often used in research technologies. There are lots of different ways we use all these different kinds of light in the sciences. So this image is a little bit more focused on quantum technologies, but in things like magnetic resonance imaging, MRI, we'll use radio frequency light, we'll use radar, we'll use microwave light. For fiber internet, we'll use infrared. For a lot of photonics and for vision, we'll use the visible spectrum. For X-ray imaging and diffraction experiments to understand how crystals come together, we'll use X-rays. And then things like the Gamma Ray Observatory will, of course, image with gamma rays to understand how the universe was formed. So that seemed to settle the debate. We know that light is a wave, we know what's waving, we know that wave has a direction, and we know what its frequency corresponds to, a color. But there's a twist to the story, in that in the early 1900s, we learned that light is actually made up of particles. So light seems to behave like an electromagnetic wave, but there are certain properties that we can't understand unless we model it as being made up of particles, and we call those particles photons. So light behaves like a wave in the sense that it interferes, but it behaves like a particle in the sense that we can actually count light. So we can't really do that too accurately. So we don't normally notice this. I think a red light bulb that's 60 watts emits something like 200 million trillion photons per second. So we're not going to notice that we can actually count them. It's very difficult to count 200 million trillion. But if we wanted to describe the results in certain experiments, actually, it was originally proposed by this fellow here, Max Planck, to describe why toasters glow red instead of glowing blue. uh, we have to model light as if it's made of these particles called photons. And indeed, if we look at things like the double slit experiment, so there's some really cool experiments you can do today. And this was actually an experiment done at the University of Waterloo in the Institute for Quantum Computing, where we did that double slit experiment that proved that light is a wave, but did it one photon at a time. So this is real data from that experiment. Each dot corresponds to one particle of light, one photon being detected, and we don't see too much at the start. But if we let it build and build and build, we eventually see that there's these regions where we see that we're much more likely to detect a photon, and these regions where we're much less likely to detect a photon. These regions of constructive and destructive interference. This is what we call wave particle duality. We are seeing this particle behavior. It is one photon at a time, but we see this wave behavior at the same time. It's always producing this interference. It is producing this interference at the same time. So in some ways it behaves like a wave, in some ways it behaves like a particle. So if someone asks you, is light a wave or a particle? You can say both, and that's not wrong. You can say neither, and that's not wrong. But you can't say one or the other. Okay, so what can we do with light? Just to wrap things up, what are some things that we can actually use light for? So, one of the things that we study here at the Institute for Quantum Computing is how we can use light to send information, these zeros and ones. Remember how we showed that light had one of two polarizations? It could be horizontally polarized or vertically polarized. Well, we could encode information into that polarization. I could send you a photon or a beam of light, and if it's polarized in this way, I could use that to encode a zero. If it's polarized this way, I'll encode a one. And in that way, I can send you a bunch of zeros and ones. I can send you a bunch of binary digits, a bunch of bits, and use that to encrypt, or not to encrypt, but to encode a very long message. Okay, and this is actually roughly what we do when we send light signals over the internet in optical fiber. We send light, we encode zeros and ones into some property of it, and then send that over long distances at the speed of light in optical fiber. We can build high-powered lasers to do a lot of really cool things. So you might have heard a couple years ago, Professor Donna Strickland from the University of Waterloo won the 2018 Nobel Prize in Physics for work in nonlinear optics. So those are special kinds of materials that can actually change the frequency of light. So right here, we're seeing this bright green light. There's actually no green laser there. What we have are two red lasers merging together to produce a green laser. And this is one of the ways we can actually boost the power of a laser is by mixing lower signals together and making them into one very, very powerful signal, which is some of the work that Professor Strickland worked on uh, over 30 years ago and resulted in the 2018 Nobel Prize in Physics for her because it's used very often both in research as well as in medical applications like laser cutting for laser surgery, for example. We can also use it to do things like laser cool things. So that's where we use strong lasers to actually trap small clusters of atoms at very, very, very cold temperatures, used in a lot of other kinds of applications and to study things like chemistry at the quantum mechanical level. On the other side of things, if we want to get away from high power and go to low power, go to these individual particles, these individual photons, we can manipulate them to perform many different tasks. One of the biggest fields of research right now in physics is quantum computing. So that's taking that information in a photon and taking advantage of some of its what we call quantum properties, these things like superposition and entanglement, to process information in different ways. When we have access to individual photons or atoms or electrons or other kinds of quantum objects, we can encode information in different ways, process it in different ways, and use that to build computers that can run different kinds of algorithms than classical computers are able to. There's also cryptographic applications looking at sending photons from Earth to a space satellite, for example, to communicate over very large distances, but doing it one photon at a time, which provides some cryptographic security by being very, very clever about how we encode that information. And there's also what we call quantum sensors, different ways that we can take information out of light by taking advantage of quantum mechanics. And one of those is actually being used at the LIGO Gravitational Wave Observatory. So this is a observatory, we see it out here, that actually sends lasers over many kilometers of distance and uses that and looks at the interference between those laser beams to detect gravitational waves, to detect small disturbances in the strength of gravity that can be used to pinpoint, for example, when two black holes merged many, many light years away. So, this is one of the most sensitive things we have to observe very, very distant and very, very weak. Um, Gravitational events, astronomical events, for example, and it all works by using light interference. It's something that will be the absolute last demo before we break for questions. So the way we are going to do that actually is we are going to take a laser beam and split it in two. Whenever we have interference, we need to split something in two. Like previously, we had the two different waves interfering with each other. So we're going to take that laser beam. So we're going to start with a laser, split it in two. So now we have two laser beams, and now we want them to interfere. So one of them is going to interact with some object. So this is something we don't know about, something that we want to learn about. And we're going to learn about it through the interference. We're going to redirect the laser beams so that they cross each other's path again. We're going to mix them again at another beam splitter, something that splits the light. And then we're going to see, did the light end up here or did it end up here? If they constructively interfere, they started off here, so they should end up right over here. If they destructively interfere, we might see the light end up where we wouldn't expect it to. Okay. In reality, these interferometers look a little something more like this. So we start off with a laser beam right here, two beam splitters that split the light, and two mirrors to redirect them. Of course, it's a little difficult to see right now, so let's spray some fog on there so you can see the laser beam path a little bit more clearly. Oh, might not be showing up too well right now, unfortunately, but you can see the laser beam a little bit there. Unfortunately, that is not showing up on camera, but we can switch to this larger version here to try to see some of that interference. Okay, so we start off with a laser beam right here. It then splits at this beam splitter, two paths, and they both exit right over here. Okay, and we can see that on the screen as so. These are the two dots from the two different ways the laser can exit. Now, if I put my hand in one, we just see these kind of blobs there. But if I unblock that, oh, let's turn down the power a little bit so we can actually see. I'm just going to go turn off the light very quickly. Yeah, now they're very nice and clear. So we see that actually. So I'm going to put my hand in to block it again. We just see two different balls. But if I have them unblocked, we see these stripes. That's that interference that we saw before in the double slit experiment. And now what I'm going to do, yeah, there we go. That looks good. So I'm just going to apply a little bit of pressure onto the boards. This is a solid metal board. I can't bend it. I'm not that strong. But the wavelength of light is, remember, just a few hundred billionths of a meter. If I apply a little bit of pressure, just with my thumb, just have my thumb right here. I'm just applying a little bit of pressure. It's making those lines move around. So by looking at the pattern there, looking at that interference, I can tell how much pressure is being applied by my thumb, which is basically nothing. And this is actually what they use to detect gravitational waves, is looking for that little tiny bit of pressure and seeing how this interference, how these lines, how these patterns change and shift. Okay. So that's all I have to show you today. Just in summary, light is an electromagnetic wave with properties like polarization. They have a color that depends on their wavelength. It's emitted in these units, in these particles that we call photons, and light and lasers are very important for many, many, many different technologies. I'd like to invite you to, if you want to learn more, there's some more on our website at iqc.ca, and also check out other events happening around the world at lightday.org for the International Day of Light. Thank you, Joe, and the Exploring by the Seat of Your Pants team for having me. It's been an absolute pleasure again, and I'm more than happy to hang around for any questions.
All right. Awesome, John. Thank you so much for an awesome presentation. I think you did a really good job of kind of breaking things down into a way that was a little bit easier to understand. And yeah, happy day, International Day of Light to you. Do you know when was that day first came to be?
Yeah, so I'm gonna mess up the year, but I want to say that 2015 or 16 was the International Year of Light. So that was
Okay.
a year-long celebration of light technologies in order to keep some of that steam going, some of that enthusiasm for the community to develop these activities and talk to people about light. It's since transformed into a yearly event on May 16th.
All right, very cool. Well, let's get into a few questions here. We have some already, but to those who are tuning in, if you use that chat sidebar, you can send in some more questions to us. Of course, let us know where you're tuning in from. But the first question I have here is from a student wondering, is there anything that can slow light down? We know how fast light moves. Can anything
Yeah.
slow it down?
That is an excellent question. And actually, many things can slow light down. So, light traveling through what we call the vacuum. So, light traveling through nothing will travel at 3 times 10 to the power 8 meters per second. That is the speed limit of the universe. Nothing can go faster than that. However, if light is traveling through a material, like say, for example, light is traveling through a piece of glass, it actually travels a little bit slower The way we think about that is that glass is made up of many, many atoms and molecules that the light enters, and then the photons that make up the light are being absorbed by the different molecules in the glass. So they spend a little bit of time hanging out as energy inside the molecules, get re-emitted as light, spend a little more time hanging out as energy inside the molecules, get re-emitted as light. And normally through glass, light travels at about two-thirds of its normal speed. There are some really, really cool experiments that try to boost this effect to ridiculous extremes using something called one of the nicest way to do it is these experiments in electromagnetically induced transparency EIT experiments. I believe the world record is that they've been able to slow light down to roughly the speed of a bicycle in these in these experiments. So they need to use very, very cold atoms, like using this laser cooling techniques. Um, the absorption of light becomes very, very, very efficient for a very, very, very narrow range of frequencies, and they can slow that light down to an incredibly uh, slow speed.
Wow, very cool. Another question here. You mentioned we only see a little bit of light, the
Mhm.
tiny, tiny little sliver, and
Just a
you
sliver.
mentioned devices, all kinds of different devices that use light that we can't see. So
Mhm.
a student here is wondering if we could see at a different wavelength, would we actually see light coming from a remote control or radio antenna towers?
Absolutely. If our eyes were perspective of that, we should be able to see it. Now then, what would we sense that as? That would be different colors. I can't say how our brain would interpret that signal. But if you've ever seen an infrared camera, for example, you might see that as people walk by, they're glowing.
Mm.
And that's because the energy that's being emitted from an object that's roughly the temperature of a human body is constantly glowing in that infrared range. So if we were able to sense that infrared range, we would sort of see people walking around as if they were basically little light bulbs all the time. The same way that when we heat up an object like our toaster, it starts glowing red because infrared light is lower energy. A lot of objects that we don't normally think about as glowing would appear to be glowing. If we could see radio frequency light, we'd be absolutely awash in the glow of that because it's so low energy that basically any object you can pick up is glowing in the radio frequency. So the visible is nice in the sense that if we could see, even a little bit more into the infrared spectrum, we'd be washed out with so much noise light. Whereas right now, only hot objects tend to glow in kind of that. Think about like fire temperatures in order to see glowing visible light.
All right. So you mentioned, light is responsible for so many different technologies. It's used in
Mhm.
so many different ways. It's used transferring information. So what is kind of next in your field? What has people most excited about the next maybe application of light? Is it in computers or is there something else people are really excited about?
So I think with light, it's going to vary a lot depending on exactly who you talk to.
Right.
There are a ton of, let's say, medical applications, so that get a lot of people excited in terms of ways that we can detect different kinds of light, the ways that we can use different kinds of light that might not we might not think about like think about like x-rays, for example, using different kinds of light to see inside the body but in different ways. One of the things that has a lot of people excited in my particular field is quantum computing, and that's where we're really controlling some of the quantum properties oftentimes of light. So either using laser beams to control things like electrons and atoms, so we can actually like have an individual atom and control the energy of its electrons using light, and really engineering the light aspects of that, uh, to build these kinds of devices. Or there are other proposals that actually use the photons, the individual units of light, um, to uh, to process this information. This gets very difficult very, very quickly. Photons, I mentioned a red light is something like 200 billion trillion photons per second.
Yeah.
So now we have one photon. Uh, if I have 200 million trillion, whatever. If I lose a few, I don't really care. If I have one photon, I need to really protect it to keep it safe.
Yeah.
Uh, so that's one of the big kind of challenges right now for the photonics community is ways to do that.
Okay. So I know there is excitement around quantum computers. What could we expect? Is it faster speeds? Is it a different way to store information? Like, how could we, where are we going to see that maybe commercially?
Yeah. So commercially, I would say quantum computers. One of the big misconceptions about quantum computing is that it's an all-purpose, let's make things faster machine. Kind of the idea that okay, quantum computers, they're 5 years away, let's say, and in 5 years, I'm going to walk into Best Buy, I'm going to pick up my laptop, and it's going to look exactly like my current laptop, but it's going to have some atoms or something in it that's
Hmm.
going to speed it up by a factor of 1,000, which is absolutely not what quantum computers are going to do. They're going to be very, very useful for solving some specific problems. And in order to get to the point where they'll be useful for solving more relevant problems for average people, that's something that is a very, very long term prospect. In the near term, what we hope to be using quantum computers for as they start to be developed is for research tasks, is for doing things like simulating other kinds of research problems, say, simulating what's keeping a material together or what conditions under which a material becomes superconducting or under which conditions a material could be used as a good magnetic memory. These kind of R&D questions in materials science or high energy physics, using the quantum computer to help us crunch those numbers, to learn more things about the universe and develop more technologies, hopefully some of which actually help us develop better and better quantum computers, so we can eventually get to solving some of these specific problems that might have relevance to the wider community.
Okay. So Mr. Hergott's class is wondering, they've got a couple questions
Oh
here,
yeah.
just along the lines of the quantum computers. Is there any form that exists already, or is development still heavily underway? Is there like some kind of prototype working
Oh yeah.
form?
Yeah, there are absolutely prototypes out there. Definitely, I would consider them working prototypes. One of the big things that people are hoping to prove right now is something called a quantum advantage. So the idea there is once we get past about 50 quantum bits, so okay, like the unit of information in a computer is a bit, a zero or one. In a quantum computer, it's the same thing. It's a zero or a one, but it's encoded in a quantum system like a photon or an atom. And once we get past about 50 or so of those quantum bits, it becomes essentially impossible for a classical computer, even a modest supercomputer, to keep up with that sort of system, but only for specific problems. So, one of the big things people are hoping for right now is to find the right problems to run on these small quantum computers that are made of 50 to 100 quantum bits that show that they can actually outperform a classical machine. And the problem being that, yeah, we may have machines that are 50 to 100 quantum bits, but they're also not perfect. There's a lot of errors, a lot of noise. So we got to kind of fight our way through the muck of those errors and noise to, uh, in order to get the right signals we want out.
Yeah. All right. So another question here from the same class. There, you mentioned that traveling through glass can slow down the speed of light.
Mhm.
Is that what happens? Does that happen in fiber optic cables?
Absolutely. Yeah. So I think I actually misspoke at some point when I said that light travels through fiber optic cables at the speed of light. It actually travels through fiber optic cables at 2/3 of the speed of light. So light traveling through a fiber optic cable is indeed a little bit slower than the speed of light.
Still really fast.
It's still really fast. Don't get me wrong. You're not going to do any better any other way.
Yeah.
But Mhm.
All right. Very cool. Well, let's squeeze in one more question here. Lucas is tuning in. Says, "Great presentation. Can you destroy light?"
Ooh. Um, so from a thermodynamics perspective, or from a let's say a conservation of energy perspective, um, energy cannot be created or destroyed. It can only be transformed. So can I destroy light? In a sense, yes. I can take that light and take its energy and dump it somewhere else. From a quantum perspective, the photons are absorbing material, but one way that you do that all the time is say you have a light bulb that's emitting energy in the form of light. Let's make it easier. So let's say we focus it with a magnifying glass kind of thing, and then I put my hand up to it, and I'm going to feel my hand get hot. And I'm going to also notice that no light should be traveling through my hand,
Mhm.
or else you probably have bigger problems. But let's assume that that's not happening right now. The light is being focused on your hand is getting hot, no light is making it through. If I took out my hand, there'd be light getting through. So the light is actually being absorbed, which I could equally well say it's being destroyed by my hand. Its energy is being transformed into heat on my hand that I'm feeling as it's sort of very lightly baking my hand, let's say. So yeah, light can be destroyed in that way, but its energy still remains. It is something that ultimately just carries energy.
All right. Well, I want to start off with a shout out to our classrooms who tuned in today. Thank you so much for sending in those great questions. Definitely some classrooms thinking about light and its properties out there. And John, thank you so much for joining us on the International Day of Light. It was really cool to see some of those experiments and really hear how interesting, unique light is with those properties kind of a wave, but also, those behaviors of a particle as well. Very cool.
Absolutely my pleasure. Thank you for having me.
All right. Well, thanks again, everyone. We are going to sign off for today, but hopefully we'll see you lots more throughout the month of May. Thanks, everyone.